Usually when we talk about making the perfect choice, there is this underlying assumption that we're looking at a finite set of options. Like you sit down at a restaurant, you read the 20 items on the menu, and you pick the best one.
Right. It's a bounded problem. If you
Yeah.
have enough time, you can evaluate every single possibility on that page.
Exactly. But what happens when the menu is literally infinite? I mean, imagine you're a business trying to optimize profit against material costs that fluctuate every millisecond.
Or, an engineer designing a microchip with billions of continuous variables. The temperature of a component could be any microscopic fraction of a degree.
Yeah. Between 100 and 200 degrees, just infinite possibilities.
Yeah.
Suddenly, checking every option isn't just difficult, it's mathematically impossible.
Traditional decision-making frameworks completely break down when you introduce infinite constraints. I mean, they're built to scan through lists, and you simply cannot scan an infinite list.
And that is exactly what we're exploring today on this deep dive. We've got some fascinating research today, including an academic review article and a presentation titled Mastering Infinite Constraints.
Really great sources.
Yeah, and our mission today is to rescue a brilliant mathematical algorithm from 1979, the Ellipsoid Method, from a wildly unfair reputation. We're going to reveal how it's secretly the ultimate tool for navigating a world of endless variables.
The overarching theme in these sources is this sort of symbiotic relationship. We're going to look at how a seemingly mindless mathematical engine, when paired with a highly specialized navigator, can solve problems that our most modern, flashy algorithms completely fail at.
So whether you are making complex business decisions, balancing a budget, or just trying to manage information overload in your own life, today's deep dive is going to show you a framework for making optimal choices without having to check every single box.
But to really understand why this is so clever, we have to look at the historical context.
Right, let's go back to 1979.
Yeah, 1979. A mathematician named L.G. Kotchian introduces the ellipsoid method. And this was a monumental moment in computer science.
Because before him, there was this huge fear, right?
Exactly. There was a fear that as certain linear programming problems got larger, the time it would take a computer to solve them would just grow exponentially, like computing times scaling into the heat death of the universe.
Wow.
But Kotchian mathematically proved that linear programming could be solved in polynomial time. He mapped it to a specific time complexity, big O of n to the fourth times L.
Big O of n to the fourth times L, which, without getting bogged down in the math, essentially proves there's a ceiling. As problems get bigger, the solving time stays manageable.
Right. It was a massive theoretical breakthrough.
But despite that, the sources highlight this huge myth that developed around the method. It basically got put on a dusty shelf because it was overshadowed by something called interior point algorithms.
Yeah, interior point methods came along shortly after. And for a very specific type of problem, I mean, they are incredibly fast.
Right.
If you have what computer scientists call a sparse matrix, meaning a lot of the data points are just zero, just empty space, and a finite number of rules, interior point algorithms will just blaze through the math.
They dart through the inside of the problem space to find the answer.
Exactly. And because of that blazing per iteration speed, the ellipsoid method was dismissed as, purely theoretical. People thought it was clunky and too slow for practical application.
I was trying to visualize the difference between the two earlier. And using an interior point algorithm is sort of like sending a highly meticulous shopper into a grocery store with a specific list.
I like that analogy.
Right, like if the list is short, they are amazing. They run down the aisle, look at the milk, look at the eggs, check them off, and they're done.
But if the grocery store is infinitely large and the list of items to check is infinitely long, that meticulous shopper will just wander forever checking individual
They'll
items.
starve to death in the store.
Literally. Interior point methods have a fatal flaw. If your problem has continuously dense, infinite constraints, they literally cannot compute it. They try to evaluate the entire infinite space at once and just crash.
Well, the ellipsoid method is a totally different kind of shopper. It doesn't check individual items. It just looks at the store and says, I am lactose intolerant and a vegetarian. I can completely avoid the entire dairy aisle and the entire meat aisle.
Yes.
It just draws a massive line and cuts those sections out of the search space. It drastically shrinks the store without ever looking at a single carton of milk.
The ellipsoid method thrives exactly where traditional solvers fail, because it requires absolutely zero explicit evaluation of all the constraints. It doesn't need to know every rule to find the answer. It only needs to know what isn't the answer.
So how does it actually pull this off mechanically? Because the sources talk a lot about this two-part system. The engine and the navigator.
Right, so the algorithm separates the labor. The engine is the search space itself, which is shaped like an ellipsoid.
You can visualize it as a perfectly symmetrical, multidimensional egg, right?
Yeah.
Encompassing all possible answers.
Exactly. And the engine is incredibly simple. Its only job is to find the exact dead center point of that egg and propose it as a potential solution.
It just holds at the middle of the bubble and says, is this it?
That is literally all it does. It hands that center point to the navigator, which the sources call a separation oracle.
The oracle.
Yeah, the oracle is a specialized piece of code that evaluates that single center point against the real-world problem. If the point is the optimal solution, great, the program ends.
But if it's not?
Right. If it violates a rule, say it requires material to be hotter than its melting point, the oracle doesn't just say no, it returns a cutting plane.
Okay, I want to make sure we're picturing this right because the math in the papers gets incredibly dense here. The formula is G transpose times X minus X0 plus beta is less than or equal to 0.
Yes.
But spatially, this cutting plane is literally just a flat slice right through the multidimensional egg, right?
Imagine taking a meat cleaver to that egg. The oracle looks at the failure and says, based on why this point failed, the answer is definitely not in this entire half of the egg. It cleanly slices the shape and throws away the bad half.
Then what happens to the remaining piece? I mean, it's sitting there with a flat side.
The engine wakes back up, looks at the remaining awkwardly sliced half shape, and mathematically draws a brand new, perfectly symmetrical but smaller ellipsoid, completely enclosing it. Then it finds the new dead center, proposes it to the oracle, and the cycle repeats.
Okay, I have to push back on this a bit.
Sure.
Because conceptually, wrapping a brand new, perfectly balanced egg around a lopsided, flat-sided half shape sounds like it would create a ton of empty dead space. How do we know we aren't just shifting this bubble around aimlessly? It feels like guessing.
You know, the early critics of the method had that exact same hesitation. It sounds computationally heavy and inefficient, but the math guarantees a rigorous reduction in the overall volume every single time. It is not aimless. The developers optimized the engine to perform this step brilliantly. In the original geometry, the algorithm uses a massive shape matrix called P to define the egg. Updating that entire matrix for every single cut would bog down the computer.
Because it's trying to recalculate billions of coordinates at once.
Exactly. So they split the matrix P into two separate parts, a volume scaling factor kappa and a core shape distortion matrix Q.
Kappa and Q.
Right. By separating the size of the egg from the shape of the egg, they save n-squared floating point operations per iteration. This mathematical trick guarantees a massive volume reduction.
How massive?
Well, if you are working in 10 dimensions, so n equals 10, the algorithm guarantees a roughly 57% reduction in the search of volume every 10 iterations.
Wow. So the net is constantly mathematically tightening. It is systematically trapping the optimal solution until there's nowhere left for the answer to hide.
And we can speed up that trapping process significantly depending on how the oracle swings the cleaver. Not all cutting planes are created equal.
Yeah, the sources break down the anatomy of a cut. The most basic one is called a central cut, which is pretty self-explanatory. The beta in that formula equals 0, so it slices perfectly and symmetrically right through the center point.
Right, it's the baseline. But then we have the deep cut. This is where beta is greater than 0. Instead of slicing exactly through the middle, the oracle realizes the failure is so spectacular that the cut can go much deeper, pushing way past the center point and excluding the center entirely.
Throwing away significantly more than half the egg in one swing.
Exactly, which leads to much faster convergence.
And there's even a shadow cut, where beta is less than 0, meaning the old center point is actually already outside the remaining half space you care about.
Yeah.
But the concept that really blew my mind was the parallel cut. Sometimes the oracle doesn't just return one slice, it returns a pair of cuts simultaneously.
This is an absolute game changer in engineering. It happens when your rules have very narrow upper and lower boundaries. Like if a radio frequency has to be strictly between a specific high limit and a low limit.
Traditional methods would make one cut, realize they're still out of bounds, run another calculation, and make another cut later.
But the specialized oracle evaluates the failure and instantly returns two parallel slices at the exact same time.
Okay, going back to our analogies, it's like playing the board game Guess Who.
Yeah.
If you ask, is your person wearing a hat? And they say no, a standard cut eliminates everyone wearing a hat. You flip down a few faces.
Right.
But a parallel cut is like asking a question that instantly allows you to flip down both the entire top row and the entire bottom row of faces at the exact same time.
You're discarding massive thick sections of the search space with a single query. It dramatically accelerates the runtime, and because of that brilliant matrix splitting we just talked about, updating the ellipsoid after a parallel cut requires at most one square root operation.
That is breathtakingly efficient. So we have this incredible engine for slicing away bad options, but the engine is essentially blind. It only knows geometry. The real heroes of this story, the reason this is actually used in the modern world, are the oracles. The sources call them the amazing oracles because they thrive on exploiting the underlying structure of a specific problem.
The ellipsoid algorithm itself is just a dumb framework.
Hmm.
The true genius is building a custom oracle that deeply understands the unique physics or the unique economics of the system you are trying to analyze.
Can we look at the economics example? The sources mention robust economic optimization using the Cobb-Douglas production profit maximization model.
Yeah, that's a great example. This is for manufacturing businesses trying to maximize profit, but they're facing interval uncertainty.
What does that actually look like for a business?
Imagine a factory buying raw steel and copper. They don't know exactly what those materials will cost tomorrow or what shipping rates will be next week. The prices are wildly fluctuating within certain high and low intervals.
Okay.
Traditional solvers will try to analyze all the thousands of potential daily price fluctuations to map out an optimal path.
Which is our meticulous shopper again.
Yeah.
Just getting overwhelmed by an endless list of possibilities.
The Oracle approach handles this entirely differently. It uses a mathematical technique called affine arithmetic to instantly locate the absolute worst-case scenario, what they call Qmax.
It finds the single most devastating combination of high prices and low demand.
Exactly. It generates a single, strict, deep cut based only on that worst case and tests the center point against it. The philosophy is, if our business model survives this exact nightmare scenario, it inherently survives all the infinite minor variations.
Wow. It just ignores the endless daily fluctuations and slices away any business plan that fails the worst case test.
It's incredibly pragmatic.
It really is. It doesn't care about mapping out every detail of the future. It just defines the boundaries of survival. And that idea of surviving the worst case scenario, it's the exact same logic engineers use to keep a physical machine from falling apart, right? The sources talk about control systems and linear matrix inequalities, or LMI.
The philosophy translates perfectly to engineering. When you're designing a control system for a drone's flight controller, you are trying to prove mathematically that the system is stable and won't spiral out of control.
Right.
To prove stability, the underlying math requires a massive grid of numbers, a symmetric matrix, to meet a specific positive condition. The Oracle uses row-based LDLT, or Cholesky decomposition, to evaluate this.
The sources mention the Oracle uses something called lazy evaluation to check this. Let's unpack that mechanism because lazy sounds like a bad thing for a drone.
In computer science, lazy just means not doing unnecessary work. A standard program will try to calculate the entire massive grid of numbers at once to see if the whole system is stable.
But the Oracle doesn't do that.
No, the Oracle starts at the top left and calculates down the rows one by one. The literal microsecond it hits a single negative diagonal entry at a specific row, say row P, it stops. It pulls the fire alarm and short circuits the calculation.
So it's essentially designed to fail fast. It's exactly like stress testing a bridge. You don't need to analyze every single rivet after the bridge collapses into the river. You find the exact steel beam that snapped first, and you focus all your energy on that failure.
And the Oracle goes one step further than just finding the broken beam. Because it stopped at that specific row P, it instantly constructs a witness vector in big O of P cubed time.
Oh, witness vector.
Think of a witness vector as a highly detailed blueprint of the failure. It is mathematical proof of exactly why the matrix wasn't positive definite. The Oracle turns that blueprint into a perfect cutting plane, hands it to the engine, and says, slice away any future designs that share this specific structural weakness.
It learns from its failures with pinpoint accuracy, without wasting time simulating the rest of the bridge collapse.
Exactly.
The sources also mentioned it doing something very similar for network theory, finding minimum cycle ratios in directed graphs for digital circuits using Tarjan's negative cycle detection.
Wherever there's a structural weakness to exploit, a specialized Oracle can find it and slice it away.
So we've talked about economics, drones, and data networks, but let's connect this to the physical device that you are probably using right now to listen to this deep dive. The sources spent a lot of time on how the ellipsoid method dominates in discrete domains.
This touches on a fundamental gap between mathematical theory and physical reality. Traditional optimization works beautifully on smooth, continuous curves. Imagine a graph where a line swoops perfectly from point A to point B.
The relaxed solution.
Right. The math assumes you can pick any microscopic point on that line. But real world engineering often requires discrete integers. You can have one logic gate on a microchip or two logic gates. You cannot build 1.5 logic gates.
The sources refer to this problem as mixed integer convex programming, or MICP. And the big real-world example they use is designing finite impulse response filters, or FIR filters, for signal processing.
Right. These are the components that clean up audio or data signals in your phone.
Yeah.
If you design an FIR filter using traditional smooth continuous math, the computer gives you a beautiful theoretical design.
But to actually manufacture that design onto a physical silicon chip, you have to use traditional multipliers to handle the decimal math.
And running constant decimal multipliers on a microchip consumes a massive amount of electricity. It drains the battery and runs incredibly hot.
So to fix that heat and power issue, engineers use a clever trick. They replace those complex, power-hungry multipliers with simple shift and add logic circuits.
Yes, by quantizing the coefficients into canonical sign digit or CSD codes. But to do that, they have to force the numbers into a rigid grid of physical hardware constraints.
And mathematically, forcing those numbers into a rigid grid destroys the smooth, continuous curve. It turns the problem space into a jagged, discrete set of points. Traditional solvers completely panic.
They do. They try to find the smooth theoretical answer and then blindly round off the numbers to the nearest physical point on the grid. That rounding error often ruins the effectiveness of the filter.
So traditional methods give you a perfect theoretical filter that is physically impossible or too power-hungry to build. But the ellipsoid method actually grounds the math in the physical reality of the microchip.
Precisely. Because the ellipsoid method relies entirely on the oracle, it handles this rigid grid flawlessly. The engine proposes its center point in the theoretical smooth space.
Okay.
But the oracle looks at that point, and instead of evaluating it blindly, the oracle reaches out and locates the nearest actual discrete solution on the rigid microchip grid. Let's call it X subscript D.
So it generates its cutting plane directly from that physical quantized point.
It completely ignores the theoretical smooth space and anchors every single cut to what can actually be built.
It just snaps it to the grid.
Yeah.
And there was one more detail in the filter design that stood out. When the system is checking to see if a frequency exceeds a required bound, the oracle uses Kolmogorov's 1939 spectral factorization.
Yeah.
Essentially, the moment a frequency crosses the danger line, the oracle triggers a cut. It doesn't have to evaluate the entire continuous frequency spectrum to know it's out of bounds. It just sets up a tripwire.
It's the ultimate pruning mechanism. Constant, efficient shortcuts that bypass infinite amounts of unnecessary calculation.
So, bringing this all together, what does this mean for the future of how we solve problems? The sources make a very definitive point in their conclusion. The ellipsoid method is absolutely not a failed competitor to the interior point algorithm.
They are not rivals at all. They form a complete ecosystem. The sources call it the complete optimization toolkit.
Like a Venn diagram.
Exactly. On one side, you have interior point solvers. You use them when your problem has sparse matrices, a finite set of constraints, and you need extremely fast per iteration speed.
But on the other side, you have the ellipsoid method paired with these ingenious oracles. You pull that tool out when your variables are discrete and rigid, or most importantly, when your constraints are dense, dynamic, or literally infinite.
It thrives in the exact environments that cause traditional computers to crash. And, the overarching lesson here goes far beyond complex mathematics and silicon chips. The core philosophy is incredibly applicable to daily life.
I totally agree. Think about the world we live in. We are constantly dealing with information overload and infinite constraints. Every day, whether you are running a business or just managing your household, you are bombarded with more data and options than you could ever possibly process.
Right.
The takeaway from the ellipsoid method is that the most efficient way forward is not to act like that meticulous shopper, exhaustively trying to analyze every single piece of data on an endless list.
Trying to calculate every variable will just paralyze you.
Instead, you need to build a good oracle for your own life. Define your absolute worst-case scenarios. Identify your critical points of failure. Use those extreme boundaries to definitively cut away massive chunks of options that just don't work.
You don't need to know the perfect answer immediately. You just need a reliable system for slicing away the noise until the right answer is the only thing left.
And if we take that philosophy and apply it to the absolute cutting edge of technology today, It raises a fascinating question about the future.
Yeah, let's leave you with something to ponder. We just saw how the ellipsoid method uses this oracle and cutting approach to guarantee finding an optimal point among infinite possibilities.
Right.
Could this framework fundamentally shift how artificial intelligence operates in the real world?
That's a huge thought.
Because right now, AI struggles immensely to navigate continuous open world environments like self driving cars on chaotic city streets, because the rules and variables are constantly shifting and infinite.
What if, instead of trying to build AI that processes every single infinite variable in real time, future AI systems are equipped with specialized separation oracles?
They wouldn't even try to understand everything happening around them.
They would just instantly generate cutting planes to eliminate paths that aren't true or actions that aren't safe, rapidly shrinking their decision space in milliseconds. It is entirely possible that the key to navigating an infinitely complex future isn't about calculating everything, but about knowing exactly where to make the cut.
Because when the menu is infinite, the only way to choose your meal is to know what aisles to skip entirely.
Thanks for joining us on this deep dive.